Hi, welcome to another EC&M Tech Talk, a series of how-to videos where we talk about everything from installation and maintenance to safety. Anyway, today we're talking really about the NEC. We're going to talk about the general installation requirements in the NEC. And you say that's Chapter 1, and you're correct. So the first thing we're going to do is we're going to go through and we're going to pull out a few items in Chapter 1 that I think are important to us that we have to pay attention to. There's one in particular about how we install our electrical equipment in this professional and skillful manner that we're going to talk about, and an informational note in that section 110.12 that it's going to refer us elsewhere. And we're going to take a look at elsewhere because not everything that we need to know to comply with our installation requirements are found in the NEC. So we're going to begin by taking a look at a few items out of Chapter 1 in the NEC. Then we're going to move into a national electrical installation standard that is referenced in the NEC, and that's the NECA1 standard, the standard for good workmanship in electrical construction. Some general information on it and an overview of NECA1. We'll pull out a few specifics. And then we want to take a look at some of these specific types of equipment and systems that are covered in our NECA1 standard. And that'll be in Section 3. And then finally, the last thing we want to look at is actually NECA 91, which is maintaining electrical equipment. Now that's an important one. It's not, well, we can look and see what the NEC has to say about maintenance of our electrical equipment, but of course the NEC is not a maintenance document. However, there's the NFPA 70B standard, which moved from a recommended practice to a standard. It's NFPA 70B, the standard for electrical equipment maintenance, so we do have to follow that one. Now, first of all, let's take a look at a few items out of Article 110 in the NEC. Of course, I'm going to use my latest edition. I've got the 2023 edition of the NEC. I'll be using that. The first thing we find is that is in 110.2. 110.2, approval. The conductors and equipment required or permitted for this code shall be acceptable only if approved. What does approved mean? Well, I can go into Article 100. Article 100 has my definitions, doesn't it? And the definition of approved means acceptable to the authority having jurisdiction. The AHJ. There's a definition in Article 100, and it's a pretty lengthy definition as to who the AHJ is. You say, well, that's the inspector. Well, it's actually more in depth than that. There's somebody, as I always say, where does the buck stop? Who further up that chain is actually the overall authority having jurisdiction for that particular area, jurisdiction, location, military base, whatever it is, righty? For instance, I recently did some code training at an Air Force base. The authority having jurisdiction was the colonel who was in charge of the civil engineering squadron for the base, and he was a mechanical engineer. Great guy, attended the class, and had a lot of great input. But he is where the buck stops, even though he had inspectors working under him. So pay attention to that definition in Article 100 for authority having jurisdiction. And remember, all of your work has to be approved. Now, the NEC goes on several different sections within Article 110 that, of course, we have to comply with all of them. I want to point out in particular two that I think are important. And so the first section that I really find that once in a while people struggle with a little bit is 110.14, specifically subsection C, which is on temperature limitations. So what are we really talking about here? Oh, if I have some number 12 AWG THHN wire. So the T tells me it's a thermoplastic. The two H's tells me that the insulation is rated for 90 degrees C, and then the N tells me that there's a nylon jacket over the outside of it, or as a covering. If I look in 310.16, which is our ampacity values, I find that this THHN number 12 wire has an ampacity of 30 amps, meaning that under its conditions of use, it can safely carry 30 amps of current flow and not exceed the temperature limitation on the insulation as the conductor begins to heat up and produce heat, the current flow through it. So that's wonderful, 30 amps of current flow. I'm now going to take this number 12, THHN, and I have just a simple duplex receptacle here, 20 amp receptacle, and I attach this number 12 THHN wire to my 20 amp receptacle. Here's the problem. This wire can carry 30 amps of current flow. The terminals on this side, right? The terminals are only rated for 60 degrees C, not 90 degrees C like the THHN insulation is. So I have a problem. If I attach this number 12 wire to these 60 degrees C terminals and allow 30 amps of current flow through this number 12 THHN, and at its rated ambient temperature and conditions of use, it will go ahead and reach 90 degrees C. However, my terminals are limited. They're only good for 60 degrees C. I'll overheat my terminals. So what do I have to do? We used to use the term derate, but if I make my adjustment, correction factors, all of those type things, and I find out that I have to limit the amount of current flow to this number 12 wire to 20 amps of current flow, because number 12 THHN in my 31016 table says that the ampacity is 20 amps on that wire at 60 degrees C. So anyway, that way I won't overheat my terminal. So I take my 30 amp wire, I attach it to a 20 amp terminal screw. I have to limit the current flow through the wire to 20 amps so I don't overheat the terminal screw, right? So that makes sense, but that's pretty much what 110.14c is addressing. Oh, and by the way, how do I know whether or not I have a 60 degree C terminal, a 75 degree C terminal, or whatever? Take a look at 110.14 and it's going to tell you based on the size and ratings on the equipment. Now, is 110.12, and it talks about the mechanical execution of work. Now, if you're familiar with that, you know, for many, many years, it's been in the code for decades, I don't know, 50, 60 years or more or whatever, and it's always said it had to be in a neat and workmanlike manner. That wording changed with the 2023 edition of the code, and now it says electrical equipment shall be installed in a professional and skillful manner. Let's talk about that a little bit. What does professional and skillful mean? I don't know, we could probably argue that one all day long. Probably one of the first things is comply with the NEC, right? If I comply with the NEC manufacturer's instructions and local codes and jurisdictions and so forth, I've gone a long way in doing my work, and certainly in a professional manner. Skillful, well, depends on how good you are at maybe running conduit or something like that, right? But there's an important informational note in 110.12, and let's pay attention to that. It says informational note. Remember, it's not a code requirement, but it does give us some important information that we need to follow, and we are going to take a look at this. Informational note, see ANSI NECA 1-2015, Standard for Good Workmanship in Electrical Construction, and other ANSI-approved installation standards for information on accepted industry practices. So, 110.12 refers me to the NECA1 standard. The latest edition is the 2023 standard. Let's take a look and see what that has to do. We'll do that in this next section then. So, the latest edition, as I said, is the 2021. It's NECA1, and once again, the title of it is Standard for Good Workmanship in Electrical Construction. What it's actually going to do for us, this standard, along with about 30 other standards that address particular types of equipment and wiring devices, conduits, and so on and so forth. If I combine all of the information in these standards together as I need it and go out and do my job, I'm going to be professional, and if I'm good at what I do, it's going to be skillful as well. So, let's take a look and more in depth at this NECA1 standard. We say that it actually defines 110.12 for us. NECA stands for the National Electrical Contractors Association, and they are the ones who publish these National Electrical Installation Standards, which are ANSI approved, which is very important. The American National Standards Institute approves them because of the method that's used in order to publish the standard, in order to gather the information. Everybody in the world has input into it, and we go in, we make our comments and so forth, and eventually it gets approved, and it becomes really what we call industry best practice. So that's what it talks about in the informational note. Now, other particular NES standards I mentioned, there's things like raceways, rigid conduit. For instance, we know we go to Article 344 in rigid conduit. We have a lot of good information about where we can use it. There's no 344.12 where we cannot use rigid conduit because we can use it everywhere. But we know that in our conduit articles, .10 is where we're use is permitted. .12 would be use is not permitted, and so forth. It gives our construction requirements in Article 344 for rigid metal conduit, but it doesn't tell us how to thread it. It gives us some support requirements, bending requirements, but it doesn't really tell us how to bend it and so on and so forth. That's where the NEIS standards pick up the ball for us. They start telling us the how to do things so that we do our installation work in that professional manner then. Now, we said that this first, the NECA1 standard, which is our general requirements, helps us to define 110.12, doing our work in a professional and skillful manner. Can't cover everything, so we have those additional NEIS standards as well. We do consider these NEIS, National Electrical Installation Standards, to be accepted industry practices. Not for commissioning, not for maintenance tasks. We're going to take a look at NEIS 91 a little bit later on, a few things on maintenance. When it comes to complying now, right, we have to have all of our work approved, acceptable to the authority having jurisdiction. We have to comply with the NEC. We have to follow all of our local codes and standards and so forth, any jurisdictional requirements that we have. Manufacturer's instructions, we always have to pay attention to manufacturer's instructions. OSHA regulations that they apply. Any project specifications drawing is really what we're going to do to go out and do our work. But once again, it may not tell us everything. So maybe my project specifications on my drawing says put a light switch. Okay? I'm going to put a light switch by the door. Where do I put it? So I have to take a box and I have to mount this box somewhere. How close do I put it to the trim of the door casing, and the height, where should it go and so forth? There's nothing in the code that says it has to be, true and plumb and all of that. And there's really nothing in the code that gives me any height requirements and so forth, but my NEIS standards do. So we're going to pay attention to them. The NEIS standard gets right up front and starts talking about you're on the job site and you get some electrical equipment, what are you going to do with it? So it talks about delivery, handling, and storage of my equipment. I should go ahead and inspect my equipment, it tells me, upon delivery. That makes sense. I handle it per the manufacturer's instructions and guidance. Store it in a clean, dry ventilation area. It's interesting, it says rotate motors if needed. That kind of rung a bell with me. So for instance, at a nuclear facility, and we had a warehouse where we stored the extra motors that we might need. And there was a requirement that every so often you had to go around in certain size motors and on up, right? You have to rotate that shaft 1 1/4 turns. Because if that shaft just sits there, maybe for years on end before that motor is installed, you're going to have bearing issues, you're going to have some possible shaft warpage and things like that. Not perceptible to the human eye, but it could be there and cause you problems. So anyway, pay attention to those types of things in our NECA1 standard. When it comes for general installation requirements, just like the NEC, the NEIS 1 standard also has some information. It says to follow the contract documents, plans, and specs. That makes sense to us. That's really not specified in the NEC. Follow manufacturer's instructions, as we said. It also says you have to make sure things are plumb and level and true. Not a requirement in the NEC, but if I've got something and it's not level or my conduit run is not straight, that's not professional and skillful, is it? And the inspector's I'm going to end up redoing that, let's say that. Right? I have to secure material with supports to exceed the expected loads. Don't just meet minimum requirements when it comes to mounting your equipment, it says. If it's applicable, go ahead and exceed those requirements. Use torque tools for threaded connections, like terminal screws, our torque screwdrivers, torque wrenches. When it comes to the things like raceways and rigid conduit, the NEIS says to go ahead and install them per the NEC, which makes sense, and the NECA standards. It says use wrench tight fittings for continuity. That's important that we make our fittings wrench tight. Now, there's no real definition for wrench tight, but the bottom line is things have to be secure when I install them. So for instance, if I have something like, take some conduit here. I've got some rigid conduit. So I've got some rigid conduit. It's threaded on the end. Those are NPT threads, National Pipe Threads. They are tapered 3/4 inch per foot. If I take those threads and now I've got a LB, same thing would be with a coupling. but there are straight threads inside of this LB. So if I take tapered threads, which are tapered on the end, right, and I start to put them in, we know, as I start to put them into those straight threads, if I were to leave that connection like that, I've got a loose connection. Mechanically, that's not good. That's not very sound. But there's another issue. In the event of a ground fault, this conduit has to carry current all the way back to the source in order to allow the overcurrent protector device, the circuit breaker or fuse, to operate and de-energize my circuit for me. So I definitely have some high resistance at this point. So I need to go ahead and make it wrench tight. So I get it secure and put a wrench on it then and make sure I've got it good and secure. And now, not only do I have a mechanically sound connection, but I also have one that is electrically sound as well. I now have that effective ground fault current path we talk about in Article 250 that will carry any ground fault current back to the source to allow my overcurrent protective device to operate. So that's important for me. Also, I have to watch, it tells me in the NEIS standard about dissimilar metals, right? I'll have corrosion. If I have corrosion, I've got high resistance. You know, an easy way you can see that, and you say, well, it's probably not that bad, you know, it's going to be all right. An easy way to see that, take a piece, go out in the field somewhere on the site and find just some rebar, some uncoated rebar. And you look at that rebar, and if it's been there a while, it's probably all rusty. Take your multimeter and read that steel. Just place your multimeter leads, set up in resistance, and try and read the resistance across that rebar. Well, it's steel, should be 0, right? Yeah, if I could go from end to end on that rebar, it's going to be 0 ohms of resistance. I bet not if it's got rust on it. Rust is a real good insulator, and you'll probably get open circuit, OL, on your meter when you try and read resistance across that rebar. I think we did that in one of the earlier tech talks a long time ago. So what happens is, if you scrape some of that rust off, you would get pretty close to 0 ohms on your multimeter then. So corrosion is a big issue for us between dissimilar metals. Not only does it damage the connection, right, mechanically, but once again, it could now provide too much resistance for that effective ground fault current path. Then I got a problem. If my overcurrent protective device up here doesn't operate when it's supposed to, I got a fire. Maybe somebody's going to get electrocuted, shocked, or whatever. Not a good situation, huh? I'm not meeting the purpose of my code to protect people and property from the hazards arising from the use of electricity, right? Practical safeguarding of all that. So anyway, pay attention to corrosion between dissimilar metals. Now, before you close things up like a panel, whatever, you've been in working inside, doing some wiring and maybe a larger control panel, make it look like a professional was in there. Take a look. Don't leave a bunch of little stripped insulation pieces down in the bottom of your cabinet. Clean it out. Vacuum it out, whatever you need to do. Get a cloth, wipe it down. Of course, it's all de-energized once you've been wiring in there, right? And go ahead and make it look good. Make sure that you don't have any tie wraps laying around, something like that. Make sure you get all your tools out of there. We probably all found that, open an enclosure sometime, and you find, oh, somebody left a screwdriver in there or something like that. Well, that's not good. Not very professional then. So make sure you do a good job when you're done. All your wiring is properly trained and so forth inside the equipment and secured, and your panel looks like a professional's been in there, okay? You think about it. You're the electrical inspector. You have to go out and inspect a panel that somebody's wired up. Maybe I've got a panel board up here, something like that. And, you know, if you take a look at it and you go, man, that looks pretty bad. I don't know, that's a mess, okay? You're not real impressed, and you might have some questions about the rest of that person's work. I certainly would, wouldn't I? But if I go on and I look at it, I'm not an expert on everything, but if I go and look at a panel to inspect it, I need to know a couple of things. And it talks about this in Chapter 1, Article 110 of the NEC. I'm going to look and I'm going to make sure all my equipment is listed and labeled. I'm not an expert. I don't know if it's good equipment or not, but if it's listed and labeled, you know, an expert on everything, right? If it's listed and labeled, then I know, okay, it meets certain testing standards, and if it's installed per manufacturer's instructions in the National Electrical Code, I can go ahead and sign it off if everything is done right, professional and skillful, because I know it'll be a good, safe installation, and that's what I'm concerned about. So 110.12, professional and skillful manner, then keep going that. Make it look like a professional wired your equipment up when you're done with it. Conductors, wires, and cables are talked about in NECA 1. It says maintain minimum bend radiuses, use compatible connectors, do not mix dissimilar metals, all those things that are pretty much common sense to us. There's going to be a lot of information on the NEC about installation of boxes in there. But once again, back to my door example, it doesn't tell me even which side of the door to put it on. Well, we pretty well know we're going to put it opposite the hinges, aren't we? That would make sense. We want to put it close to the trim. How close to the trim, to the finished trim, wherever that's going to be? About 2 to 12 inches from the trim, 3 inches from the door frame. Now, typical mounting heights, we want to maintain consistency. It's not specified in the NEC, but best industry practice tells us things like on receptacle data outlets, I'm going to mount those at 18 inches from the center of the box down to the floor is what I'm going to do. Now, for things like switches, it's 48 inches. Thermostats, fire alarm, pull stations, 48 inches. However, the NEIS standard also says to take a look at the Americans with Disabilities Act and see what your mounting height should be. Right? For instance, on panel boards, it tells me that from the center of the grip, right, of the operating handle down to the floor, that disconnecting device would have to be no more than 6 feet 7 inches above the floor. That's in the NEC under our disconnecting means. Now, the NEIS1 standard also gives us that same information from the highest breaker in that panel, no more than 6 feet 7 inches off the floor, unless it has to comply with the ADA requirements, and then it's going to be 48 inches is going to be the maximum off the floor. Kitchen, utility room receptacles, we should be mounting those 42 inches off the floor from the center of the box to our floor level and 6 inches above countertops and whatnot. Follow your specifications, follow your local jurisdictional requirements, best industry practices, and so forth. These are the NEIS1 requirements. I could take all this information we're talking about and go back to what? NEC Article 406 is on receptacles and cord connectors and attachment plugs. And I could take a look in Article 401 on luminaires and lighting. I could take a look in Article 314 on my outlet device and pull boxes and find all of my detailed installation requirements that I must comply with. But 110.12 says I better consider my best industry practice as well. Grounding systems is also covered in the NEIS1 standard. Of course, we have Article 250 and as well as different grounding and bonding applications throughout the code. We have to ensure electrical continuity. We've talked about that a little bit, about making up fittings securely and so on. We use listed bonding methods. We install electrodes per the NEC, it tells us. And of course, the NEIS standard does reference, obviously, different NEC articles throughout it. And it also, there's a separate, by the way, NEIS standard 331 on grounding and bonding. Probably want to pay attention to that one. As far as my ground rods, my grounding electrode system, it talks about making my actual connection to the ground rod. It should be flush or below grade. It also talks about connections for our grounding electrode system. And the ones that they list in the NEIS standard are the same that we have in 250.8 for connections to grounding and bonding. You know, listed pressure connectors, terminal bars, exothermic welding, machine screws, have to make at least 2 threads of engagement and so on. So anyway, you can always refer, obviously, to 250.8. You're definitely going to comply with that. When it comes to connecting grounding electrodes, using the water pipe, as I should say, as your grounding electrode system, it also something it mentions in the NEIS standard, and this was an issue, discussion point anyway, over the last few years with 250.70, where it says my ground clamps shall be listed for the materials of the grounding electrode. And so if I'm going to a galvanized water pipe and I have a copper grounding electrode conductor and all of that type of thing, and going to a copper ground rod, make sure that the listings on your clamps are applicable to whatever type of material that you're going. Let's move into the next section and talk about some of the specific systems and equipment that we have in the NEIS standard, that are addressed, as I should say, in the NEIS standard. Now, for instance, in the NEC, we have 2 articles on battery systems. Also, Chapter 14 in the NEIS addresses the installation of battery systems. And in the NEC, we have Article 480, which is for the installation of storage batteries. And then we also have Article 706, which is energy storage systems, which includes batteries, right? But there are other types of energy storage systems as well, addressed in 706. The way that now, so those cover our installation requirements. But the way that NECA approaches this Chapter 14 on battery systems is safety. And it tells you, I can't turn a battery off, can I? There's no switch I can flip on a cell, and maybe that cell is, I don't know, I measure it and it's 2.25 volts or something like that. Great big old battery cell, right? And you go, well, that's way below, 50 volts, man. That's a safe working voltage. It's only, 2.25 volts or 2.5 volts or whatever it is. But what about the energy inside of that thing? If we were to actually accidentally get a wrench or something across those terminals, extremely dangerous. So the NEIS standard addresses that. It talks about cell voltage. It talks about PPE. Bottom line, if I'm going to wear PPE working in a battery room, dress for the most prevalent hazard. People say, well, do I have to wear an arc-rated face shield? Well, think about what you're doing. I don't want acid, and that's the most prevalent thing that's probably going to happen if it's a wet cell, a lead acid cell. I don't want acid to get on my face. So if I'm adding some water or acid, whatever, into that battery, I want to make sure that I'm protected against from that most prevalent hazard. But we have to consider the electrical hazard, certainly. My tools are going to be insulated. I also have to consider hydrogen. Something like a lead acid cell produces hydrogen gas, doesn't it? And that can be extremely flammable in certain concentrations. So ventilation in my battery room becomes important. How to install my rack. When I put my cells in the rack, I always start from the center and work out, the NEIS tells me. Chapter 15 of the NEIS 1 addresses the installation of solar photovoltaic systems, PV systems. And it's primarily mechanical. It also addresses NECA, or references NECA 412, which is strictly on the installation of PV systems. So it talks a lot about manufacturing instructions, using stainless steel mounting hardware. So I mount directly to the center of that rafter, so I get a good mechanically secure connection. Work with my roofers, secure or seal any penetrations I have through the roof. So that's the type of information that's addressed in Chapter 15 on PV systems. Following manufacturer's instructions that emphasize it and so forth. Also to protect the output circuits, because remember, a solar panel, if it's got light on it, I can't turn that off either. It also talks about the importance of the disconnecting means that's addressed in the articles on the PV systems as well. Wind turbines, same thing, lots of mechanical installation. You think about those great big huge wind turbines, and what are your hazards? I'm working at heights. Okay? I have a lot of mechanical hazards involved. Electrical wiring, I'm going to follow what? Chapters 1 through 4 and any NEC article like 694 on my wind electric systems for installation. So follow all of those special rules. Let's take a look as we wrap up here in our last section. Let's take a look at NECA 91, NEC 91. The latest edition is the 2023 edition once again. And it's titled Maintaining Electrical Equipment. Now, we already mentioned our NFPA 70B standard went from a recommended practice to a required standard in the 2023 edition, right? And so we have to comply with 70B. I really like this NECA NEIS standard on electrical equipment maintenance. It gives me a lot of good practical information. It reminds us that the reason that we do maintenance is to keep our installations safe and reliable, yeah. The main thing is safety. If I go out to work on electrical equipment, I want that equipment to be safe, and the owner of that equipment certainly wants it to be reliable, doesn't it? Reduce downtime. It talks about inspections, testing, repairs, and preventive maintenance on my electrical equipment in the NEIS 91 standard. It tells me always to follow manufacturer's instructions. It says still to follow NFPA 70B. It talks about general information for doing electrical equipment maintenance, safe work practices, but not the safe work practices from the NFPA 70E. It talks about the practical everyday work practices, heights and closed spaces, confined space entry, those types of things that we work with when we're doing electrical maintenance, or different situations we're involved in. It talks about de-energizing electrical equipment. We say, well, we go to Article 120 and we put our equipment in that electrically safe work condition. Lock it out, tag it out, man. Make sure it's dead before you stick your hands in there, right? Very important. It talks about safety in battery systems once again. We've already mentioned some information in Chapter 14 on that. It talks about that SF6 gas, that we use for insulation in some of our medium and high voltage equipment like breakers and switches. That's that sulfur hexafluoride, and it can be very caustic if it leaks out of the system and forms a white powder. And I can have enough moisture, understand, just in my dry fingers, that when I touch it I can make an acid out of it, and of course that can create injuries as well. So anyway, covers a lot of information then. It talks about the inspections that we have to do. It lists about 50 different types of electrical equipment in the NEIS 91 standard. It tells us to go through and what to look for in visual and mechanical inspection. It talks about all the different types of testing. It has an excellent informative annex on testing practices that can be of value to you. So a real good document to maintain your equipment, NEIS 91 then. So, to wrap things up, okay, remember we have to comply with the NEC, project specifications, drawings, local codes and standards. We have to follow manufacturer's instructions when we install our electrical equipment. Got to comply with 110.12, and how do we do that? In order to make sure our work is professional and skillful, we use the NEIS standards. They're best industry practice. Those are going to define that 110.12 for us. And then, other than that, we have to maintain our equipment to keep it safe when we go to work on it, and follow our safe work practices when we're out there doing our work. So anyway, until the next Tech Talk, be safe.